Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in the next module we will right away start with to begin with the laws of multiple interaction. Okay, so the laws of multiple interaction. Laws of multiple interaction. So suppose we have particles P0, P1, P2, Pn. So suppose we have, I should say n minus 1. So suppose we have n particles, Pi's, and these particles are interacting with each other with respective forces, right? So suppose we have particles all interacting with respect to each other and all other influences are removed, right? So we have particles all interacting with each other and all other influences are removed. Then the acceleration in A0 induced by P0, by the particle P0, are such that A0 is going to be the sum of the rest of the acceleration induced by the other particle on the particle P0, right? So we rename these as A0i's, I from 1 to n minus 1. Okay, so I from 1 to n minus 1. So these are the respective. So let me draw the figure to highlight what I just mentioned. So we have particle P0 here interacting with, let's say, P1, P2, P3 and so on, P4 and so on, right? So we see that these particles are interacting with its neighbors and their respective acceleration due to the interactive forces are A01, A02 and so on. So the net acceleration on this particle under consideration is the sum of all the individual acceleration due to the individual interaction with other particles. Well, most important in this rule of the law of multiple interaction is the so-called principle of superposition, right? So superposition principle. Superposition principle, which says that if we have multiple particles available in a given setting and they are all interacting with each other, then the net motion or the net acceleration is as if we can individually find out the acceleration due to two different particles, assuming that the other particles are absent, and sum up individually all these contributions, right? So that is the principle of superposition. That is, the individual interactions can be added assuming all the other interactions are absent, and that creates this linear law of superposition. Okay, so then if we multiply, let me call this law as law number 1, and then if we multiply 1 with mass m0, we see that we are going to get that the net force acting on the body is F0, which is equal to F10 plus F20 and so on, plus F0 n minus 1, right? So the net force acting on the mass, on the particle P0 is the sum of the individual forces due to interaction with the other particles. Okay. So from here we can start to derive some useful concepts. The first important concept is the concept of center of mass of a particle. Okay. Okay, so the center of mass in layman's term is nothing but the weighted position of the particle in an environment in which it is interacting with other particles. Okay, so center of mass is a point in space, well, typically 3D space, where is a point whose position vector r is defined by r given by m1 r1 plus m2 r2 plus mn rn. Okay, divided by m1 plus mn. Okay, so this is the weighted average of the position vectors of the particles, right? And we see that this is, in short, we can write this as, this is equal to mi ri by summation mi, or the sum of the masses. Let me call this as a summation mi as some giant mass capital M, right? Well, a quick example is, suppose all the masses are equal, the interacting masses are all equal, then the center of mass will not contain, the formula for center of mass will not contain any mass. Let us see how, let us see this issue through one example. Okay, so what I just said is, suppose we want to find the center of mass of three identical particles, and then we see that the center of mass is given by summation mi ri divided by m, right, where m is nothing but, now we see that all the masses are equal of the particles, so we can take the mass m out of this summation, and this m, let's say it is three identical particles, so I will be from 1 to 3 and capital M is 3m, 3 small m. So we see that the final answer is devoid of any mass in the system, right? So for identical masses, we should not get any mass in this formula for center of mass. Okay, so with this ideas, let us now start diving into the concept of laws of gravitation. Okay, laws of gravitation. So what we see is that the force, the law of gravitation says is, what it says is that the force exerted on the two particles of masses, let's say small m and capital M, upon each other is m1 m2 g by r square, right? Well, I would say not m1 m2, but the two masses are small m and capital M. Okay, so typically if two masses are interacting, we will always have this so-called law of the gravitational force. This is always present because of the gravitational field which is present all around us, right, where r is typically the distance between the two masses, right? Okay, so well, this question is, if this gravitational force is all around us, all of us are experiencing this force, then how come we don't feel the effects of gravitation? Why can't, if two masses, they are interacting, typically this gravitational force is attractive in nature, so we have a minus sign, right? The minus sign indicates attractive in nature. So if we have a gravitational force which is attractive in nature, why are masses not attracting with each other? Why are you, the readers, not attracted to me and come out of the screen and get attracted to me? Why is this law of gravitation not preventing our interaction, right? So this question comes, the answer to this question lies in the fact, if we look at an example, as to what is the scale or what is the magnitude of this law of gravitation, right? So let me just show you with an example. So suppose if we have two masses, let's say m1 is 5000 kgs, right? So typically that is much more than the weight of a person. So let's say m1 is 5000 kg and m2 is also equal to m1. We take two identical masses, and then we have that this capital G is a constant. This is a constant. G is given by 6.67 into 10 to the power minus 11 Newton meter square inverse kg square inverse, right? And when we plug everything, let's say these masses are separated. They are separated by a distance. We can keep a normal distance, let's say by a distance 1 meter. So r is equal to 1 meter, right? Typically, this is the typical order of distances of the masses on Earth, right? So we see that if we find this this gravitational force, let's say Fg, we will see that Fg comes out to be roughly equal to it comes out to be 10 to the power minus 3 Newton. Okay, roughly 10 to the power minus 3 Newton. So this is a minuscule force. So that is what I am trying to highlight. Even for such large masses, we see that this force fails to perform its fails to show its effect because the force is very tiny, right? Now typically this force is going to act if we talk about bodies of the order of with masses of the order of the satellites. For example, typically the gravitational forces acts on large bodies like Earth or Sun. So typical masses are let's say the mass of the Sun, which is roughly equal to 2 into 10 to the power 30 kg, the mass of the Sun, right? And then similarly, then if we plug these sort of masses, we are going to get significantly or sizable values of the gravitational force, right? So then, let us now dive into some more practical examples related to these gravitational forces of attraction. So one practical questions of interest is, what about the law of gravitation on continuous distribution of masses? So continuous distribution of masses. Continuous distribution of masses. Let me highlight this point with one example. So suppose we have let's say two masses. Let's say mass 1 is fixed at some point C, and this first mass is has a value m. This first particle of mass small m, this is interacting with two particles of masses, let's say capital M, right? So this is the setup that we have. We have two masses of capital M which are joining, which can be joined with a straight line of distance 2a, right? And let's say we have a third mass which is at a distance of x from the line perpendicular to this line which is joining the two masses capital M, right? And we want to find the gravitational forces acting on this system. So this question is, find f of g for the system. Okay. So we see that we have already seen that from the law of gravitation, that the gravitational forces always acts along the line joining the two particles, right? So we will have set of two gravitational forces which we have to add to find the net answer. One is this gravitational force, which is, let's say, I call this as Fg1, and the other is this gravitational force Fg2, right? These are acting along the line joining the two particles. So then if we are going to add these two, so remember this is going to be a vector addition of the two forces, we see that there will be two components of each of these two forces. Let me also fix the axis of or the axis of our inertial frame. So we have the x axis and the y axis. So along the line of distance 2a we have the y axis, and along the y axis the two forces, since we have the two masses which are equal, the gravitational forces along these two lines will be equal, right? So we see that Fg1 will be equal to Fg2. Why? Because Fg1 and Fg2 both involves the same masses, or masses with the same, or particles with the same masses, right? So these two gravitational forces will be equal, which means that if we were to find the y component of these two gravitational forces, they are going to cancel each other. Why? Because they are equal, and the y component, let's say we call this theta, so the sine theta component, they are going to cancel each other, and only we will have the net gravitational force which is going to be along the x axis, and they are going to add up, they are each going to add up, right? So we have to keep the arrows very clear. So here we have the arrows acting on the two particle, right? So then we see that we have to find the net gravitational force is 2 times Fg1 times the cos of theta, right? So this is the angle theta which the line joining the two masses makes with the horizontal axis or the x axis. Then our net force is going to be the following, and this net force is acting along the line I hat, where I hat is the unit vector along the x direction, right? So we have so the answer to this problem lies, now we are going to start to plug the values. We see that this is 2 times m times capital M by times g by r square. Well, r square, let me keep this r square, the distance between, well, not this distance. So we need to find this particular distance r, right? Because that is the distance joining the two masses, right? And so we have that r is going to be square root a square plus x square, right? So if we have Fg1 is mg m capital M g by r square times cos theta. So cos theta is going to be x divided by r, right? And then we find that the net force, gravitational force, is mg by x, and now r is the following. We plug the value, we see that this is equal to a square plus x square to the power 3 by 2. And finally we see that these gravitational forces are attracting. I mean, we have to quantify, or we have to clarify what do we mean by attracting here. We just say, let us say to begin with, we assume that capital M is larger than small m, right? So we expect that the mass which is larger is going to attract the mass which is smaller, right? So that is hence the direction along the larger values of m. So since our gravitational force is attractive, we put a minus sign to show that this is acting along the negative x direction, right? So that is how we typically predict the gravitational forces of attraction between the point set of masses. Okay, so then what do we have? Then what do we have is, I just want to show you one more thing. Notice what happens. Let me rewrite this expression as follows. So this is 2m capital M g by 1 over 1 plus a by x square to the power 3 by 2, right? And we see that suppose in this particular setup, if we have that a over x is small, when can this happen? This happens when the distance between the third mass, when we have these two masses, capital M and capital M, which are separated by distance 2a, and the third mass, small m, is at a infinitely large distance, small x, from the two masses, we see that this particular gravitational force is going to come out to be, well, have we missed something? We have divided by x, so we have to, this is 3 by 2, so we have to divide by x square also, right? So this net gravitational force comes out to be by as follows. So what is the moral of the story here? The moral of the story is that suppose the third mass is kept at a distance which is very far from the two masses, capital M, then our net gravitational force is as if, this is as if the gravitational force for point masses, So for sufficiently large distances, we can see that this gravitational force acting on this system is going to be as if the masses were point masses, right? They are not bodies. We can completely neglect the structure of the masses and assume that these masses are point objects. They are kept at singular points at distances small x along the x-axis and a along the y-axis, right? So these are gravitational forces for point masses. Okay, so enough of that. Well, then let me now formally try to show you what happens to the gravitational force for continuous distribution of masses, right? So what am I saying here? So what I am saying here is that suppose we have the gravitational force by a uniform rod. So now we are going to talk about objects which have continuous distribution of masses, right? So if we have this following, right, and then if so we have a rod, let me say this rod has, well, this total rod has some length, let's say capital L, and we have the mass of this rod, let's say this mass of this rod is m, so the mass is capital M, and then at a distance small b, we have another particle which is kept and this particle has a mass which is given by small m, and now we have to find the gravitational force of this system, Fg. So instead of two point masses which are kept at opposite ends along the y-axis, so let me also fix my frame of reference. We now have a continuous distribution of mass in the form of a rod. So let us say that the rod has a mass, m. So the rod has a mass m, and let us say the mass per unit length of the rod. The mass per unit length, let's say, is going to be capital M over L. Right? Now suppose we want to find a mass of an infinitesimally small portion of the rod, right? So we see that the mass of an infinitesimally small portion of the rod dx, so let me call this the mass per unit length. So now if we want to find the mass of a small portion, this is going to be dm, d is capital M, right? It's going to be mass per unit length times the small portion dx, right? So now what we have been able to do is we have been able to translate our problem from the continuous mass distribution to a point mass distribution, where each points, we can assume the rod is made up of infinitesimally large number of points of masses dm, which is given by this following formula, right? And then again for the small mass, infinitesimally small mass, we can start to find the net gravitational force of attraction, right? So we will see that well, actually it helps and it makes sense if we keep L to be equal to 2a, right? So where a is our half the length of the rod. So mass per unit length is m over 2l, m over 2a times dx, right? And then we see that the net force acting, the net gravitational force acting on this mass distribution is going to be small m times small m times d capital M times g divided by r square cos of theta. So that is where my cos theta is again this angle theta, and my r is the distance between the infinitesimally small mass dm and small m, right? And we have to multiply it with 2 and put a minus sign. And why? Because this is the same setup of the problem with discrete masses that we have solved a few minutes back in the previous slide. Okay, so then what we have is now let me just plug in all these values. So small dm, so we have minus 2 times small m times capital M by 2a divided times dx times g divided by r square cos theta. So this quantity is going to be b divided by b square plus r square times 3 over 2, right? So that is my answer to this gravitational force for this infinitesimally small mass, right? Now the problem is this r, well, something is wrong here, so that is what I was saying. So this r is going to be, what has happened? So this is b over b square plus x square, where x is this distance. So our r is depending on this horizontal distance x of the particle small m from the rod. So that is what we have in terms of the formula. And now we to find this gravitational force Fg, we are going to integrate this entire infinitesimal force m over 2a times g times b times dx divided by b square plus x square to the power 3 by 2. And now notice that we have taken in this calculation, since we have multiplied by 2, we have taken two equal masses and added up its contribution from the top and the bottom, and hence it was making sense to keep the length 2a, right? So since we have added contribution from two equal and opposite masses, we have to keep the integral from 0 to a and not from minus a to plus a, because we have already put in a factor of 2. So when we integrate all this, we are going to find the answer to be the following. The listeners can please go and check that this is equal to b times b square plus a square to the power 1/2. Okay. So that is the answer as far as when we are concerned about the continuous mass distribution, right? Similarly, we can talk about continuous mass distribution for uniform disk. So how far we have progressed? Well, we can talk about the gravitational force due to a uniform disk. Gravitation by a uniform disk. Okay. So now again, instead of a rod, now we have a disc, and a disc with the center, let's say O, and now the disc is interacting, let's say, with the particle P, which is kept at a distance small b, and this distance is b, which is perpendicular to the uniform disc, right? And then let me now complete all the geometric basics of this diagram. Let's say we take a small mass, well, it's a disc, so we take a small mass dm of the disc, and this dm is making an angle, well, it is at a distance small r from the disc, and let us say that we have this particle P is making an angle, it is making an angle alpha with respect to this small mass dm. Remember, this particular angle, which is the angle along this along this axis, and the angle made by this radial distance is 90 degrees. So we have alpha being the following, and now we are ready to write down the gravitational forces, the infinitesimal gravitational force due to this small mass dm, which is at a distance r. So we see that this small mass dm, we have to see what is the mass distribution. So the mass distribution is, let's say this disk has the total mass capital M. So the mass distribution dm is going to be m over a times dA, right? So we have the following. So this is m over a. So a is pi, let's say what is my radius of the disk. So let me say that the radius of the disk is a. So a is the radius. Okay. So m over a comes out to be m by pi a square, and dA comes out to be r dr d theta. So that is my area element for the disk, right? Area element for the disk. And then what we see is that what do we have? We see that f comes out to be hold on. So that is my small mass. So from here I can find the infinitesimally small force Fg. So Fg comes out to be will be dm times let's say this well, I think I've messed up the notation here, so I need to call this as d capital M, because we have a capital mass m, and so now we have a d capital M, and this particle is of mass small m, right? So now the gravitational force is d capital M times g divided by 2, well, what is the distance here? Let me call this distance as r square. What is this r? R is this r, right? The r, which is the distance along the line joining the two masses dm and small m. So what do we have here? So let us now plug in what are the different values. We have that this is equal to well, are we missing something? Let me just zoom out this figure. Okay, so this figure is that we have this center O, and we have this particle which is of mass d capital M. So this is dm, and this is subtending an angle alpha, right? This is hold on. Well, we need to talk about the setup on the disk. Okay, so what we have is we need to see this setup on the disk. So we zoom out this mass m, right? So let me call that we have to first fix the axis. So let me say that this is my x-axis and my y-axis is along this mass small m. So this is my axis. So this d capital M is making, suppose it is making an angle theta with the x-axis. So now we see that So if this d capital M is making an angle theta with the x-axis, right? And then what we have is that this particular mass is also having a small angle d theta, right? And then so that is the same d theta that we are talking about here. So what we have is now the net gravitational force comes out to be dm. So dm is m divided by pi a square times dA, which is r dr d theta, right? And then small m times capital G divided by capital R square. So capital R square is going to be well, there is also the fact that this force is acting along the line joining the two masses. So we need to project our forces from this particular line to this y-axis. We see that this is also equal to cos of alpha, right? So from here we have r square cos alpha, and this particular quantity comes out to be, from the geometry, comes out to be b divided by b square plus r square to the power 3 by 2. Okay. Have we missed anything? I don't think we have missed anything. So now all that is left is we need to integrate this gravitational force, and since this is an area integral, we have to integrate r. So r is from 0 to the area of the disk A, and theta is from 0 to the total angle 2 pi, and inside this integral we keep this quantity, and then once we integrate we get the answer as follows. This is going to be 2m capital M G by a square times 1 minus b divided by a square plus b square. Okay. Okay. So then, so that completes the discussion on the gravitational force by a uniform disk. So let us now wrap this discussion for this particular module, and in the next module I'm going to talk about we will continue our discussion on more uniform objects, for example the one due to spheres, right, and see how our answer changes. So thank you so far for listening.